the exam. So I will see if I have to add some other formulas or not. But yeah, so I've added the formulas for stress transformation, for angles, maximum stresses, if you want to calculate Mohr circle, if you want to do the yield criteria and the coulombs. And these are the previous formulas to calculate the stresses. So in exam, I will give you a beam or some member. So you have to extract stress element for yourself. So for that you need stress formula. So if it's a normal force, you need this formula. If it's a bending moment, you need this formula. If it's shear force, you need this formula. If it's torsion, you need to calculate stress using this formula. And also in these formulas, you have moment of inertia. So if it's a square, you need to calculate moment of inertia from this formula. So that's how it's gonna be. And if someone asks you to calculate displacement, you can either use the sheet I have given you, or but I'm not gonna ask you to calculate the deflections. But I mean, you still have to use these formulas to calculate stresses. So first you have to calculate reactions, and then you have to calculate the internal loads at a specific point, and then you have to calculate stresses. And once you have those stresses, then you have to extract the stress element. We will do this today. So exam is gonna be kind of similar what we will do today, and also there's gonna be a quiz on Monday, which is gonna be on a similar pattern, and then we'll have exam on Wednesday. So whatever we'll do today is super important, and same we'll have quiz on Monday, and also exam is gonna be on a same pattern. And I will cross verify if the formulas are correct, and if I have to add some formulas, maybe because Q, you all know, in order to calculate this Q, you need to calculate A star, Y star prime. So during the weekend, maybe you can revise your previous chapters, like how you calculated those stresses, how to calculate moment of inertia. But in exam, the shape is gonna be simple. It's gonna be square like before. So you need to know how to calculate moment of inertia. You need to know how to calculate stresses. And in order to calculate stresses, of course, you need to know how to know the internal loads. And for internal loads, you need to calculate reactions. So it's like comprehensive. Everything we have studied in this entire subject is gonna be part of exam kind of in this way. So this is how it is. So we can start. And also about the exam, we're gonna have three questions like before. So the first question would be, I will give you a member. So for example, this is what we were doing before, right? So it's gonna be in question, there's gonna be something, a beam with different loading condition like we had before. So you will have the beam, and you will be asked to calculate the reactions and calculate the internal loads. That's going to be question one. And also stresses, right? So the question one would be calculate stresses because of the loads. So the stresses could be because of shear force, because of bending moment. So that's going to be question one, calculating stresses from the member. So if you have this kind of configuration, we'll have shear force and bending moment. But if I apply a load also, then you will also have axial stresses. So you have to determine all those stresses from the member, and that's going to be question one. And in question two, once you have those stresses, you're going to do you're going to extract the stress element. So in question two, you have to extract stress element, and then you have to do all those things: stress transformation, calculate maximum principal stresses, draw the Mohr circle, these kind of things. That's going to be question two. And question three would be, once you have those maximum stresses, then question three would be to figure out if it's going to fail or not. So I will give you yield stress, and then you have to figure out failure using von Mises and Tresca if it's a ductile material. But if it's a brittle material, then you have to use Coulomb theory. So we're going to do all this today. So we're going to practice we're gonna finish example 11.3 today. So it's gonna you guys will have a clear understanding like how to extract stress element and to do more circle and to figure out if it will be a failure or not for a given member. And on Monday we're gonna have exam. So on Monday we're gonna have quiz. So I will give you a different uh, beam, and then you have to do everything what we will do today. But for quiz, it's gonna be like you guys can discuss with each other also. You guys can ask me questions if you want. So in quiz, it's gonna be not very strict, but then we'll have exam on Wednesday. So so I would say this example is important, and the example and the quiz is important when it comes to exam. And in exam is gonna be a different uh, configuration, different loading scenario. So in this case, we only have one force applied at the edge, right? But in the exam, it's going to be a different loading situation. But the idea is the same. So this is the last example, which is really comprehensive. It just touches various concepts we have studied along the way during our course. So this is what we were doing before. So what we have to do in this case is this is a cantilever beam with a force 12 pound. So we have to figure out basically that will this beam will fail or not under this 12 pound of force. So this is what we are doing here. So what we have to do is we have to figure out if this is safe or under this load, this cantilever beam will yield or not. So that's what we are trying to figure out. We are trying to figure out if this is safe or not. So for this, in order to figure out if this is safe or not, we have to basically use the yield criteria. And this is a ductile material, so we have to use von Mises or we have to use Tresca. But in order to use von Mises and Tresca, we have to basically use these von Mises and Tresca. But for that, we need stress 1 and stress 2. And we can only get stress 1 and stress 2 using stress transformations, right? Mohr circle stress transformation. So we need the stress element. And stress element we can extract once we have the stresses. So that's why we need to calculate stresses first to extract the stress element. And once we have the stress element, we can do all those things to figure out if this beam is safe or it's going to yield or not. And stresses comes from internal loads. So that's why we are drawing those shear force and bending moment diagrams so that we can determine those internal loads. And then from there, we can extract the stress element. And from there, we can compare the yield criteria. So first step was to calculate the reactions we did last time. The next step is to draw shear force and bending moment diagram because from there we can determine stresses. So this is what we did last time. We also draw shear force diagram and bending moment diagram because under this load, that's the only things we have. If it would have in some other loading condition, we would have something else as well. But in this case, we only have shear force and bending moment. So we know that at this point, we'll have, so shear stress is same along the entire length. So we don't have a problem. But bending moment, if you go away from the fixed support, your bending moment keeps on decreasing. So you'll have maximum bending moment at this point, right? So that's the point where you'll have maximum bending moment and the shear stress is same. So we're gonna select this point because if failure will happen, it's gonna happen at this point because that's where you'll get the maximum bending moment. So at this point, our shear force is 12, our bending moment is negative 432. So we know uh, how to calculate stresses from this, right? We have to use these two formulas to calculate stresses. So we have to use this formula and we can calculate stresses from these internal loads. Down the three stress elements. So our next part is draw stress elements at A, B, and C. So at A, let's just call this top fiber. Top fiber. B is the stress element B is at quarter of a height. And C is at neutral axis. Neutral axis. So we're gonna say this is top fiber, so TF. This is quarter height, so QH. This is neutral axis, so NA. So we have one stress element at top fiber. We'll have another stress element at quarter height, and we're gonna have another stress element at the neutral axis, because we don't know which one will give us the maximum stresses. So at point A, this is point A, right? So at point A, our axial stress is 10,000 psi. So this is our normal stress, right? So normal stress is also in tension. So our normal stress is in tension, and this normal stress as X is actually 10,368 psi. And our shear stress is zero at that stress element. So this is what we will have. So this is the stress element at point A at the top fiber. So at the top fiber, uh, this is the top fiber. So you can see the axial stresses. You have the axial stress is in tension, and the magnitude of that axial stress is 10,368, which are these stresses. And the shear stress at that point is zero, so no shear stresses. At point B, so at point B, our axial stresses, the normal stresses, sorry, the normal stresses are 5184 psi, and you also have a shear stress 27. So your shear stress tau xy is 27 psi. And at point C, your normal stress is zero, but shear stress is 36. So there is no normal stress, and your shear stress is tau xy is 36 psi. So we have extracted three stress elements, and we don't know which of the stress element will give us maximum stresses. So since we have to compare it with the yield criteria, so in yield criteria, the formulas include, I can show you the formulas as well. So these are the formulas for the yield criteria, right? This one and this one. So, we need stress 1 and stress 2 to calculate the yield criteria and to see if the failure is going to happen or not. But these, so we have to calculate stress 1 and we have to calculate stress 2. You can also calculate tau max if you want. Stress 1, stress 2, and tau max. So stress 1 and stress 2 and tau max. So you guys can try to calculate and give me the values. What values are you getting from this? So there are two ways to do this. One is, so there are two ways to do this, right? One method is first calculate theta p, which is going to give you the angle where you'll get the maximum normal stresses, and use the transformation equations. Then you calculate theta s, that will give you an angle where you'll get the maximum shear stresses, and use the transformation equation. The second way is just use this one. Just use this equation, you're going to get stress 1 and stress 2, and use this equation, you're going to get tau max. So one method is to use transformation equations, another method is just to use the equation for the maximum. So in this case, since we don't need to draw the stress element, we just need to calculate the loads, the maximum stresses. So I think it's more suitable to use these equations. It's going to be super fast. It's going to save a lot of your time. But if someone would have asked you to draw the stress elements where you'll get the maximum normal stresses and the maximum shear stresses, then you have to use the transformation equation. So I would suggest you guys can use this equation, and you can give me stress 1, stress 2, and tau max. So I guess this should be easy because we have been doing this for a while now. So I'm gonna just write it down, the answers I got So stress 1 is 10,368 psi. Stress 2 is 0. Tau max is 5,184 psi. For the quarter height stress element, our stress 1 is 5184 psi. Stress 2 is 0. Tau max is 2592 psi. In this case, our stress 1 is 36 psi. Stress 2 is negative 36 psi. And tau max is 36 psi. So these are the maximum stresses you're gonna get at that particular point, right? So at point A, which is top fiber, the maximum stress 1 is 10,368 psi. So you can extract a couple of observations. You can see a couple of observations from here. For example, I think the stress 1, the top fiber, is the most dominating one, because if you see the stresses, the maximum you're getting it is from the top fiber, 10,368. And if you look at shear stresses also, although it had no shear stress, it had shear stress, and it also had shear stress. But if you look at the maximum shear stresses, the maximum shear stress also, we are getting it from the top fiber, 5,184. Here also, this stress element has like not a lot of stresses. This stress element has some, but this stress element has the highest amount of stresses. So I think this is going to be the dominating one, but we can keep on doing for the rest of it as well. So what we can observe is if failure will happen, it's going to happen at the top fiber. So if you keep on increasing the load, you're going to have you're going to break this cantilever beam at this point, and the break will start at the very top because that's where you're getting the maximum stress. So if I want to draw the entire beam, so that's where it will kind of break, because that's where we are getting the maximum stresses, right? So that's the first point of break, and then it will like break, the entire thing will break. But we will see if we will observe the yielding or not. Breaking, I mean, it will yield, but then it will break because it's a ductile material. So it will fracture at a very, after deforming a bit. So we have the stresses now. So now what we can do is we can figure out failure. So we can use Tresca and we can use von Mises because it's a ductile material. So we can write down this is our top fiber, this is our quarter height stress element, and this is the stress element at neutral axis. So for Tresca, I'm gonna write down the yield criteria, and for von Mises, I'm also gonna write down the yield criteria. So the yield criteria for Tresca is, let's just write down here. So for Tresca, we know the yield criteria is stress 1 minus stress 2 should be greater than or equal to yield for failure, or stress 2 minus stress 3 should be greater than or equal to yield for failure, or stress 3 minus stress 1 should be greater than or equal to yield for failure. That's Tresca. And for von Mises, we know that our von Mises stress, which is stress Vm, that should be greater than or equal to the yield. And our formula for von Mises stress is stress 1 minus stress 2 whole square plus stress 2 minus stress 3 whole square plus stress 3 minus stress 1 whole square divided by 2. So this is what we have for the yield criteria. We did this last time. So what you can give me is this stress VM, 1 meter stress for top fiber, for corner height, and for neutral axis. And also from Tresca, you can calculate those stresses and you can put the maximum here. And you can give me the values for this. So stress 1 for top fiber is 10,368. Stress 2 for top fiber is 0. And stress 3 is also 0 for top fiber, for all the stress element, because it's a two-dimensional stress element. So stress 3 would be 0. So in question, the yield stress was given, right? Y was given, which is 35 KSI, which is equal to 35,000 PSI. So that is our capacity. This is the maximum stress this material can endure, can take. So our stresses are way below this maximum capacity. So our material is safe. So our stress element is not yielding, so the material is safe. So that's how you check. So basically, we can put a lot more load than it's already there because our stress is kind of like 3 times less. And also, we can calculate, which is something which is called safety factor. So safety factor is how safe our member is uh, with respect to the maximum stress it can take. So the formula for safety factor is yield stress by allowable stress. So our yield stress is 35,000 psi, which is the maximum stress our member can take without yielding. And our maximum stress is 10,368. So the safety factor in our case is 3.37. So it means our stresses are like the maximum yield stress is 3.37 times higher. So the capacity is 3.37 times higher than what stress we are experiencing. So we are quite safe here. Next, we can, it says draw Mohr circle. And I mean, we have been doing Mohr circle, so everybody understands how to calculate Mohr circle. So we have 3 stress elements. So we're going to have 3 Mohr circle. So I think you guys can do this on your own. The next question was draw yield surfaces. Yield surfaces. So just like Mohr circle is a graphical representation of our stress elements, the yield surface is also a graphical representation of failure surfaces, and we can also graphically see if a failure will happen or not. So I'm going to draw yield surface for von Mises, and I'm going to draw yield surface for Tresca. So we touched this a little bit, but I'm going to just draw this. So we know that to figure out failure, we need to know stress 1 and stress 2. So in all the equations in von Mises and Tresca, we had stress 1 and stress 2, and that's how we figured out failure. So that's why I'm going to plot stress 1 and stress 2 on a plot. So we know if the stress 1 is higher than, so I'm going to plot yield point. So yield point is that point, that's the maximum capacity, the maximum stress it can take before yielding. And I'm going to put negative y here. This is yield here, this is yield here. So these are those points beyond which, if you go, you're going to yield, right? So Tresca yield surface, it says you can draw Tresca yield surface by making a box. and then you have to draw straight lines here. This is our Tresca yield surface. And if you draw parabola around it, that's our von Mises yield surface. If it's a brittle material, so you have Coulomb yield surface, which is basically a box. We don't need this, but this is gonna be our Coulomb yield surface. So the idea is, if your point lies outside the yield surface, then you will consider it as a failure. But if it lies inside the yield surface, then it's not a failure. So we already have top fiber, we have fiber at quarter height, we had fiber at neutral axis. We already know what are the stresses at top fiber, what are the stresses at quarter height, what are the stresses at neutral axis. So the stresses at the top fiber are 10,368, and this is 0. The stresses are 5184, and this is 0. And the stresses are 36 and negative 36 psi. So we used equations, but we can also use the yield surface. So we can plot this on a yield surface and we can see. So in this case, our stress 1, stress 2 coordinate, which we're going to plot it on a yield surface, is 10,368, 0. So this value is basically 35,000 psi, right? So this 10,000 should be somewhere here. This is our top fiber. And if you want to plot our quarter height, it's going to be somewhere here. This is quarter height. And if you want to plot the neutral axis, it's 36 and minus 36. It's going to be somewhere here. This is our neutral axis. So you can see that's the maximum capacity, and our stresses are like quite in a safe range. So that's how you draw yield surfaces. And the part F they're asking is to calculate deflection. Deflection of beam. So it's a cantilever beam with a load. So one way is to use these equations. This equation will give you like angle, and this equation will give you displacements. You can use this equation, or you can use the paper I gave you, and it already had a formula for on this. So you can use this formula directly. I'm going to write down the formula. So if you want to calculate deflection for a cantilever beam with a point load, the formula I gave you a paper, and the formula on that paper is negative PL cube over 3EI. So you can use this formula. If you use this formula, you're going to get 1.79 inches of deflection at the end of a cantilever beam. I mean, you can calculate this. P is actually 12 pound of load, length is 36 inches, modulus of elasticity was given, which was 10,000 KSI, and moment of inertia you can calculate. So that's how we can analyze any structure So to summarize, uh, we were asked to calculate, uh, to figure out if this cantilever beam under 12 pound of load will experience yielding or it's safe. So we calculated reactions first, and then we calculated shear force and bending moment diagrams. From this, we figured out a point where we need further investigation to calculate stresses. So from the internal loads, which is shear force and bending moment, we calculated stresses, right? So once we have those stresses, we can draw those stresses along the cross section, because the stresses are not constant along the cross section, they change. And from here, we saw that when shear stress is maximum along the cross section, axial stress is zero. But when axial stress is maximum, shear stress is zero. So we don't know where we'll get the maximum stresses. So we kind of extracted three stress elements, right? A, B, and C. So if you extract those three stress elements, this is how they look like. And then we have those stress elements. We determine the maximum stresses based on the rotation. What will be the maximum stresses we'll get? So these are the maximum stresses which we will get. And so now we are clear that the stress element A is more dominant, because that's where we'll have maximum shear stresses and maximum normal stresses as well. So at stress element A, we calculated von Mises stresses, which is a combination. If you combine, you have to combine stress 1 and stress 2, you'll get the von Mises stresses and Tresca stresses. And we can compare these stresses with the yield criteria, with the maximum capacity. So these are the stresses which we are experiencing because of the 12-pound load. But we have to compare it with the capacity of material. So material capacity is 35,000 psi. So if the stresses exceed 35,000 psi, then we will experience yielding in a cantilever beam. But since these stresses are low, so we are safe here. And we can also calculate the safety factor. So we are safe by this much amount. So we are more than 3 times safe. We can also draw yield surfaces. We can also calculate deflection. So that's how it is. That's how you check if your designed member is safe under a given loading condition or not.